When we gaze into the cosmos, we're not simply looking at the stars and galaxies that inhabit the universe. We're peering into the past. Through this cosmic window, we can unfold the tale of the universe. Initially, it was a realm of high-energy particles, rapidly expanding, and eventually giving birth to galaxies and countless structures. But as we trace the echoes of this cosmic evolution, we stumble upon a surprise, something unexpected, something that's reshaping our understanding of the universe itself. Now, this cosmic interloper appears to be pushing galaxies away from us, making them recede at an ever-accelerating pace. This mysterious energy lurking in the very fabric of space is known as dark energy. And believe me when I say it's far more intriguing than it sounds. But what it exactly is and its implications, hold your horses, we'll get to that soon enough. What's up, my fantastic and curious folks? Ready to unravel some mysteries today? It's your favorite deep diver Cesar here, and with me as always is our very own commentator extraordinaire, Sonia, who's just as eager to dive into today's topic.
Hi everyone, I hope you're ready to have your minds blown today.
Don't forget to subscribe to our channel, folks. Hit that bell icon so you don't miss out on our daily episodes. Stick with us as we journey into the vast and infinite cosmos of knowledge, here on the Curiosity Wonderland. Let's take a step back and imagine ourselves not as human beings, but as omnipresent beings who existed during the earliest moments of the universe. Think about having the capability of keeping track of two different locations at all times. One of those locations would be where our Milky Way galaxy will eventually be formed, and the other would correspond to a distant galaxy, not gravitationally bound to anything in the Milky Way's vicinity. Now, at the start of the hot Big Bang, the universe was rapidly expanding, teeming with densely packed, high-energy, ultra-relativistic quanta. An early phase dominated by radiation gave way to several later stages where radiation was still present, but not as prominent as before. All the while, matter began to clump into gas clouds, stars, star clusters, galaxies, and other structures. All this while the universe continued to expand.
So we're talking about an incredibly dynamic and evolving universe here, right?
Absolutely. And as we look further and further into the distance, we're seeing those objects not as they are today, but as they were billions of years ago. Their light has journeyed across vast cosmic distances, being stretched by the expanding fabric of space itself. This process of stretching is what causes the light to redshift, or shift towards longer wavelengths. By studying this redshift, we've been able to learn how the universe has expanded throughout its history. We've discovered that the universe isn't just expanding, but that distant objects appear to speed up faster and faster as they recede from one another. This is the phenomenon we call the accelerated expansion of the universe. And it's through this that we discovered dark energy and measured its properties, forever changing our understanding of the universe.
That's astonishing. So we're essentially picking up signals from the universe's past. It's like the universe is telling its own story.
Exactly. And what an incredible story it has to share. So, if you've kept track of these locations from the initial moments of the hot Big Bang up until now, you'd witness some intriguing changes. These two locations would expand away from each other, and the rate of cosmic expansion and the properties of these regions would evolve over time. Initially, no light signals would be able to move freely from one region to another. We'd need to wait until the universe was about 380,000 years old, as that was when the universe became transparent to light.
Hold on, you're saying that before that age, the universe wasn't transparent to light?
Exactly. It was only after reaching that age that the cosmic microwave background, initially visible, would fade to infrared and then microwave wavelengths. As time passed, we'd see molecular clouds form and contract, followed by the birth of stars and black holes within a multitude of early nebulae. These would merge into proto-galaxies, which would then merge, gravitate, and grow, evolving into full-fledged galaxies like we see today. This evolution would lead to the formation of modern-day galaxies, undergoing long, quiet eras punctuated by bursts of star formation.
So the galaxies we see today are the results of an incredibly complex and dynamic evolution process. starting right from the Big Bang itself?
That's correct, and younger galaxies that resemble the Milky Way are inherently smaller, bluer, more chaotic, and richer in gas than the galaxies we see today. For the earliest galaxies, this effect is even more extreme. As far as we've seen, galaxies adhere to these rules.
Wow, it's just stunning to realize the enormous changes the universe has undergone from its early stages to now.
Now, let's talk about redshift and blueshift. When light from distant galaxies gets stretched to longer wavelengths, we see it as redshifted. If it gets compressed to shorter wavelengths, it's blueshifted. But for distant galaxies, we almost always observe a redshift, and this redshift generally increases with distance.
So the farther away a galaxy is, the more redshifted it appears to us.
That's correct. We can measure both redshift and distance across a wide variety of objects and use these measurements to reconstruct the history of the expanding universe. Now, the data from supernovae, specifically, has been pointing towards a universe that expands in a way that needs something beyond matter, radiation, and spatial curvature, a new form of energy that drives expansion, which we call dark energy.
Dark energy. That's just fascinating. Is that why even the most distant supernovae adhere to the standard cosmological model?
Yes, exactly. In reality, we aren't omniscient. We can only make observations at one point in space and time. However, by observing the distance and redshift of different objects across the universe, we can infer how 2 points in space recede from one another over cosmic time. When we observe the light from a nearby galaxy, its light is redshifted by the amount that the universe has expanded from when that light was emitted until we observe it. The light from a more distant galaxy is redshifted by a greater amount. As we accumulate more objects at greater distances, we can use this data to understand how the universe has expanded over cosmic history.
So, by studying redshift, we're actually learning about the history of the universe.
Precisely. And because the way the universe expands over its history is determined by the different forms of energy present throughout the universe's history, we can also learn what the universe is made of. Now, let's delve deeper. If we plot a graph of the apparent expansion rate against distance, we find that the universe expanded faster in the past, but distant galaxies are accelerating in their recession today. This extends much farther than Hubble's original work. The points on our graph do not form a straight line, indicating a change in the expansion rate over time. The curve that the universe follows is indicative of the late-time dominance of dark energy. Once we know what the universe is made of, we can use this information to understand how various forms of energy evolve with time. This helps us answer our initial question: what would we see if we could track a single galaxy's distance and redshift throughout the history of the universe? In the earliest stages, the light that first arrived from a distant object would tell us its distance and its redshift. The distance would have been relatively small compared to what we see today, while the redshift would have been quite large. This redshift, if we interpret it as a Doppler shift, can be made to correspond to an apparent recession speed, how quickly the object appears to be moving away from us. However, it isn't the object's motion causing the redshift. It's the fact that the light is traveling through the fabric of space, and the fabric expands while the light travels, that causes the redshift we observe. Initially, the distances to other extragalactic objects would be small while the redshifts would be large. We would infer that this distant galaxy is speeding away from us at a very rapid rate. As we let time march forward, both the distances to and the inferred velocity of those objects would significantly change, but in opposing directions. The distances gradually increase as the universe continues to expand, pushing all objects that aren't gravitationally bound away from each other. From any one galaxy's perspective, all distant, unbound galaxies continue to move farther away as time goes on. This results from the universe's changing expansion rate, which depends on the total matter and energy density present. As an increasing volume implies a decreasing energy density, the expansion rate drops, and the distant galaxy appears to move away from us at a slower speed. Picture this: light may be emitted at a particular wavelength, but the universe's expansion will stretch it as it travels. Ultraviolet light can be shifted all the way to the infrared when considering a galaxy whose light has been traveling for over 13 billion years. You can understand this better if you think of the expanding universe in the context of the Big Bang. There's a cosmic race taking place between gravity, striving to pull everything back together, and the initial expansion rate, working to drive everything apart. This race has been going on for roughly 13.8 billion years, with the Big Bang serving as the starting gun. If there were too much matter in the universe, everything would expand only up to a point before the expansion reversed, and things began contracting. This would lead to a cosmic event known as a big crunch. Conversely, if there were too little matter, the expansion would continue forever, with the expansion rate decreasing but never stopping or reversing. And then there's what we could call a Goldilocks scenario, where the universe lives right on the edge between those two prior outcomes. Now imagine the universe expanding forever, but the expansion rate approaching zero. If we add just a single atom to the universe, it would recollapse, but without that atom, things just keep expanding, albeit as slowly as physics allows. The Big Bang alone offers no explanation as to why the initial expansion rate at the universe's birth balances the total energy density so perfectly, leaving no room for spatial curvature and a perfectly flat universe. For billions of years, an individual galaxy appears to move away from us at an incredibly fast rate, but then its recession speed drops as the matter and radiation densities decrease. However, after a few billion years, something unexpected happens. Instead of approaching zero, the expansion rate starts to decrease at a slower rate, causing distant galaxies to recede from us more quickly. There's a strange parallel to this in something I recently experienced. I was driving my car up a steep hill. At first, I needed to push the gas pedal hard to maintain my speed, much like the universe's expansion was initially fast. But as I reached the top of the hill, my car's speed started to decrease, mirroring the slowing rate of the universe's expansion. However, once I started to coast downhill, the car started to accelerate again on its own, reminiscent of how the universe's expansion is now accelerating.
That's a great analogy. Coincidentally, I recently had a similar experience while blowing up a balloon. At first, I had to blow really hard to start the expansion, resembling the initial rapid expansion of the universe. But as the balloon got bigger, the rate of expansion slowed down. And then, once it reached a certain point, the balloon seemed to expand more easily, almost as if it was self-accelerating. Just like the universe.
The mysterious force causing this acceleration in the universe is what we call dark energy. Its nature is still unexplained, and it remains one of the biggest mysteries in cosmology. The laws that govern these phenomena, known as the Friedmann equations, link the universe's expansion to the types of matter and energy present within it. This data and these observations tell us something profound. The universe isn't filled only with matter and radiation. We also need something else, something new, dark energy. This form of energy is inherent to space itself. As the universe expands, dark energy doesn't dilute, but rather maintains a constant density. Everything else, including all forms of matter and radiation, dilutes as the universe expands. After 7.8 billion years, the matter density drops far enough that the effects of dark energy start to become significant. It reaches the critical value to cause a distant galaxy to stop decelerating from our perspective and begin accelerating instead. This reminds me of a recent experience I had with a helium balloon. Initially, the balloon floated upward, battling against gravity, akin to the early expansion of the universe. But over time, the helium inside the balloon started to leak, representing the decreasing matter density. However, because the balloon remained inflated due to the pressure difference, it stayed afloat. This resilience likened to the constant energy density of dark energy.
Interesting. I had a similar experience with a rubber band. Initially, I stretched it quickly, but then the tension made it difficult to stretch further, similar to the universe's rapid early expansion and later deceleration. However, after a point, the rubber band seemed to give a little, allowing me to stretch it further with the same force, just like the accelerating expansion due to dark energy.
As the universe ages, distant objects not bound to one another recede at an increasingly faster rate. When the universe was 9.2 billion years old, around the time our solar system was forming, the matter density had already dropped below the dark energy density. Today, 13.8 billion years after the Big Bang, dark energy accounts for about 70% of the total energy in the universe. And as time goes on, that percentage is going to increase. When the universe reaches twice its present age, dark energy will account for over 95% of the universe's total energy. Now this is where it gets really interesting. For the past 6 billion years, the universe's expansion has been accelerating. This means that any distant galaxy we monitor appears to recede from us at an ever-increasing speed. Any galaxy currently at a distance of approximately 18 billion light-years from us now appears to recede away faster than the speed of light. This means there's nothing we can ever do to reach or contact it again. Given that the universe is already 46 billion light-years in radius, this means that 94% of the galaxies in the universe are already forever beyond our reach. Now, when you think about it, it's fascinating. For billions of years, dark energy's density would have been tiny compared to the density of matter, meaning its effects would have been undetectable if humans had arisen too early. It's only because we came along when we did, at this golden cosmic time, that we can perceive what the universe is actually made of. Dark energy is real, began dominating our universe at an age of 7.8 billion years old, and it determines our cosmic fate from here on out. So there you have it, dark energy, a phenomenon that has transformed our understanding of the universe. It's a cosmic force inherent to space itself that remains a constant density even as the universe expands. It began to dominate when the universe was 7.8 billion years old, and now accounts for approximately 70% of the total energy in the universe. The existence of dark energy tells us that the universe is not just expanding, but accelerating. And this cosmic acceleration has pushed 94% of the galaxies in the universe beyond our reach, forever. It's a story of light, time, and the constant race between gravity and expansion. It's a mystery that has challenged the brightest minds and will continue to determine our cosmic fate. All of this makes me think, if we were to run a universal marathon, we'd better get ready to race against dark energy.
And that's some race we're up against, isn't it? But isn't it exciting to know that we're living in a time when such cosmic phenomena can be observed and studied? There's so much to learn, so many mysteries to unravel. Thanks for joining us on this journey through the cosmos. If you enjoyed the episode, don't forget to blast that like button and leave us a comment. We'd love to hear your thoughts about dark energy and other cosmic mysteries. Remember to share the episode with your friends so they can join the cosmic conversation too.
And with that, we're signing off. Keep wondering, keep exploring, and remember, the universe is full of mysteries waiting to be solved. Goodbye, everyone.
Goodbye and stay curious.
This intriguing information was from an article titled, "What Was It Like When Dark Energy Rose to Prominence?" on the bigthink.com site. The article was published on January 31st, 2024, and written by Ethan Siegel. The full URL is in the video description if you want to delve deeper into the subject. All right? Now, I'm off.